distinguished guests, esteemed colleagues, ladies and gentlemen, I am Doros Theodore, professor of the National Technical University of Athens and member of the Academy of Athens and the US Academy of Engineering, and it is my honor to welcome you to this session on natural and human-triggered mega disasters. Few topics cut so sharply across scientific disciplines, public policy, and human vulnerability. We live in a period where extreme events, earthquakes, tsunamis, floods, droughts, cascading climate impacts are no longer anomalies. They are becoming defining features of our century. Some are purely natural in origin, others are amplified, triggered, or transformed by human activity. But all of them test the resilience of our societies, the adequacy of our scientific understanding, and the effectiveness of our preparedness and response. Confronting such challenges requires interdisciplinary and international efforts. Today's session brings together three world-leading scientists whose work spans the physics of earthquake rupture, the science and governance of early warning systems, and the hydrological extremes reshaping our planet. Their perspectives are complementary, but also different, and it is precisely in this intersection that real understanding emerges. So it is my privilege to introduce our first speaker, Professor Rosakis of the California Institute of Technology. Professor Rosakis is one of the most distinguished experimental mechanicians of our time. He's a member of the Academy of Athens, of the National Academy of Sciences, of the National Academy of Engineering, a foreign member of the Royal Society, a member of the Academia Europea, of the European Academy of Sciences, of the European Academy of Sciences and the Arts, of the American Academy of Arts and Sciences, and of the Indian Academy of Engineering, a constellation of honors that reflects the global impact of his work. At Caltech, he served as the Theodore von Kármán Professor of Aerospace and Mechanical Engineering, as the Director of GALCIT, and later as the Dean of Engineering. Professor Rosakis pioneered laboratory methods that revealed the physics of Supershear's rupture, a phenomenon once considered theoretical, but now recognized as a key factor in some of the world's most devastating earthquakes. Today, a few days after the third anniversary of the devastating Türkiye, Syria event, he will examine whether supershear dynamics played a decisive role in this extraordinary lethality and what this means for future seismic risk. Please join me in welcoming Professor Rosakis.
Thank you very much for a very kind introduction. As you probably understood, I'm scientifically confused in the sense that I'm an engineer, but I'm also a geophysicist of sorts. The underlying thing between what I do and other geophysicists do has to do with the instrument, which is mechanics of materials. So, mechanics is going to be the tool that I'm going to be using to discuss the extremely destructive and lethal earthquake that happened in Turkey, in the border between Turkey and Syria, in February 6, 2023. Now, I remember very well waking up later the next day and hearing that this devastating earthquakes had happened, and it caught my attention immediately. The initial images were amazing, very disturbing, and you can see in the background of the first slide the type of thing that has happened. I'm going to show you many more of these images, unfortunately. But what we did at the time is I actually called my team and contacted people that would be interested and had knowledge of the ground. And one of them was Professor George Gazetas from the National Technical University of Athens. The other one was Professor Ahmed El-Bana, who is the director of the Southern SCEC, Southern California Earthquake Center. And the other one was a Turkish professor from Istanbul, Esref Galkinyaya, who had access to the seismic records in Turkey. And we started immediately looking at this phenomenon because we were suspecting the connections that may exist between this phenomenon and some of our older laboratory findings going back almost 30 years ago. So I'll try to make a connection with this. First of all, though, before I continue, I would like to extend my condolences to the Turkish and Syrian people for this horrific event, which classifies to be the fifth most destructive and lethal earthquake in modern era. So let me start with some images. First of all, 3 years ago and 3 days, so last Friday was the anniversary, there was an earthquake event that ruptured 300 kilometers of the East Anatolian Fault. You will see a map in a second, what is the East Anatolian Fault. A second one, which was almost as big, 7.7 in the Richter scale, occurred 9 hours afterwards. Now, you see the level of destruction here, which is amazing. These are the first images that were coming out of Turkey before we had an idea of what the total damage was and where it was. In this particular case, the photograph comes from Antakya, the ancient Antioch, and they were shocking. Now, I'll tell you a few things about the earthquake. The main shock lasted around 70 seconds. And overall, the earthquake sequence resulted in horrific human loss. And what is officially known is about 60,000 people were dead very quickly, perhaps half of them within 35 seconds of this. And 1.5 million were displaced. And this made this event really special in the mechanics of catastrophes. So the damage exceeded $118 billion, and the scientists could not understand exactly what happened. And one of the reasons was the fact that a lot of damage was accumulated and a lot of deaths happened at extremely long distances away from the hypocenter. And this is a very key thing to remember. Just a few more ideas of how it looked and how it felt. It was a fantastic event. Again, big structures, new structures collapsed, but it was really selective. And I'll go, and this is from one particular part that I will show you in the map. The tectonic setting, first of all. You see these lines are faults. And I'm an engineer by training, and I study fracture fracture in metals, fracture in rocks, but also the big ruptures that are the earthquakes that create the shaking. To me, they are very similar things. So these lines are very important because those are the lines along which the earthquake rupture will propagate. To me, the hypocenter is almost irrelevant. In the sense, what I care is about the zipper that will unzip these lines. Because the way that I understand the earthquake as an engineer is if you have a sweater and a zipper, and you want to zip your or unzip your sweater, the zipper has to move with a specific speed. And it is the speed of the zipper that creates the shaking in neighboring areas close to the faults. These are faults between the Anatolian plate in Turkey and the Syria, the Arabic plate, crashing against each other. To orient you, the red dot is close to Istanbul. It is in Izmit, or Nicomedia, and it was the site of a horrific event in 1999 that I will refer to later. But the new earthquake that I was telling you about started on the bottom to the right here, on the East Anatolian fault. The North Anatolian fault is on top. The East Anatolian fault is where the dots are. It propagated in this segment towards the city of Antakya. You see the Gulf of Alexandretta on its left. So, I will show you how we know where the faults are. Roughly, when there is a big earthquake, there are aftershocks, many hypocenters that are activated along the lines, and they actually paint the lines for us. We have other ways to actually understanding where the lines are. But in this particular case, what I would like to show you is that there is a star there. There is a line, a red line on the bottom. There is another one, a red line on the top, and another star. I'm going to concentrate on the first earthquake that started from this star, and there is a small line above this star that connects it to the main line. The main line is the main fault, but the little line that comes to it is what is called the gnarly splay fault. You should think, again, with the analogy of the zipper, or an analogy that has to do with a car driving into an on-ramp to a highway. The zipper climbed on the little fault. It met the main East Anatolian fault and had a choice to go right or to go left. And mechanics will tell the zipper where to go. And that's the important here. Why am I interested in this? Because at this particular case, we have a great advantage. It was luck. You see all these green triangles. Those are seismic stations that are all along the lower part of the fault. And this is a unique situation. The drama of seismology is that we don't know where an earthquake will happen, in what fault. We don't know when. We know very little. Prediction is not in reality these days. So it's very rare to have a situation like this. That's why and also have results that are available, and I would like to thank the Turkish authorities for making these results available. Now, let me go to the next one. Here is the same map, and again, you see the fault, but you see something else. the population distribution in relation to the fault plane. And to me, as I said, the hypocenter is not what's important. What's important is the location of the fault. And I wanted to show you that, again, the star, the little line on top of it, and I'm actually going to go and show it to you here. The little line that goes from here to there is the Nardi fault. And then the earthquake, actually, we know, went to the right, and then went to the left, all the way to Antioch. Antioch has an amazing record of historical earthquakes, as Professor Koinon testified. So, having this in mind, the first observation was, how come that the biggest destruction in this particular geometry does not happen near the hypocenter? It happens 150 kilometers away. So this shows you the importance of actually the zipper and the speed of the zipper. The speed of the zipper is something that I have been studying for a long time in relation to composite materials, where the zipper is between two materials that are connected, a metal and a polymer, and they are subjected to some dynamic loading. And again, you have a path, δρόμο, a path that will capture the earthquake, and it will go along the zipper. In engineering, there, at that time, we were able to see that there are certain behaviors that do not exceed in monolithic materials, but exist wherever there is a fault, wherever there is a weak line, a line of weakness. So, just to make sure that I cover this very quickly, unfortunately, a lot of rich heritage was lost in Turkey. You see the before and after photographs of mosques and castles. This is an ancient castle that was built by Emperor Justinian. And here is what happened, some of the things that happened in Antakya. I don't want to give a history lesson. I just wanted to continue. And basically, now I'm ready to shape the basic questions. The basic questions, the specific questions are, why was this event so destructive, especially very far from the hypocenter? Why did the rupture jump from the little fault into the main Eastern Anatolian fault? And would this level of destruction be associated with the issue of the zipper speed? Whether this zipper speed was what is called in scientific jargon, supershear. So what is supershear? Supershear is a zipper speed that is so fast that it exceeds the speed of the characteristic, one of the characteristic wave speeds in the solid, in the rock to the right and left of the zipper or the fault. And that, in a sense, makes it equivalent to a supersonic aircraft that exceeds the sound speed of air. But actually, solids, unlike fluids, have two characteristic wave speeds, the shear wave speed and the dilatational wave speed. The pressure wave speed is the faster one, and the shear wave speed is the slower one. This thing, a supershear rupture, exceeds one of the two, or it becomes intersonic. So, but for years, the existence of these phenomena in seismology was actually doubted because we didn't have the stations to prove it. So this particular event, despite the fact that it has changed the life of thousands of people, it, in one sense, affected our lives as well, because it was the first living proof that our conjecture that what we have seen in the laboratory will be seen in real earthquakes was proven. So that's my mission today. So here we are. We have the fault line. The little dots are stations that we're going to scrutinize, and we're going to characterize them as super shear, uncertain, or what is called sub-Rayleigh. Sub-Rayleigh is a speed, Rayleigh wave speed is a speed close to the shear wave speed that was discussed by Lord Rayleigh many years ago. But this is the picture here, and again, we start from the little star, and we go up. So the rupture, the zipper will unzip here. There are two stations, two sides here, not enough here. And then you go to the right and left, and you see what we do as what the speed is as it goes down. I think you can, yeah. Oh, actually, fine visitor. So, I'm going to concentrate on the little fall first, because I know certain things about it, and I'm going to use it to understand the properties of rock and the properties of friction. I know the geometry, I know the tectonic loads, and what I notice here is, first of all, something very fortuitous, that there is a station, if you refer to the white square to the right, which is a magnification of the other one, you see two stations together. Those I will call twin stations, and you see another station just below it. Now, the existence of the twin stations is very important because I am an experimentalist, and I would like to have the luxury of having two measurements from two places that are, at least two places that are very close to each other for a sanity check. So the twin stations are very important, and then just behind them there's another station. So here are the twin stations. What I'm plotting here on top is the fault parallel shaking. So the zipper is going and along the fault, and there is shaking in the parallel direction and shaking in the vertical direction. And the fault parallel shaking is on the top, and the fault normal shaking is at the bottom. And you see two lines. One line is one of the twins, and the other one is the other of the twins. And what is soothing to me is that it seems that this is a real signal. So, how is this relating to the experiment? Just a small parenthesis here. So this is the experimental setup. This is work that I did with Professor Kanamori, who is the person that introduced the moment magnitude scale Caltech, famous seismologist. And this is an experiment this size. So we're going to do experiments that are Mickey Mouse experiments of some sort, and we're going to get conclusions out of them. Hopefully they hold for something much bigger. So in this experiment, what you see is two pieces of plastic that are brought together, held in frictional contact, under pressure and shear. And they are waiting there because the angle is less than the angle of friction. And we have high-speed cameras that you see on the top, and optics, cameras that are capable of 1 to 10 million frames per second. This is very high speed because we have to capture everything. And when I click, you will see something happening. The star is the epicenter, but how do we create an epicenter? We want to start an earthquake, but not load it through this. So we insert a copper or a nickel wire, the size of a human hair, in there, in a very little hole. We hold it by 2 clicks, and we discharge a capacitor, creating just a small burst of plasma that only lasts for 5 microseconds. And what you will see things happening to the right and left. And let me start clicking here. A rupture will go to the right and to the left at the same time. And in the beginning, you see the waves that are emitted. The pressure wave is one of them, and inside are the shear waves. And again, you see a circle, and you start seeing actually some structure. And again, this is classical, because you see the circle, and you see things behind it. You see here things that are starting to shake. Everything is slower than the circle. But if I continue clicking, you see that there are triangles that are formed. So something has exceeded the circle, which is the shear wave. And so the zipper has now gone in front of the circle, becoming supershear. And you see the two Mach cones, which are equivalent to an aeroplane that has exceeded the wave speed of pressure waves, and creating a sonic boom. But now, this is not a pressure boom, it's a shear wave boom that is related to the shaking of the buildings. So you can continue this, but you see what happens is that there is a transition distance that takes you from the classical idea of earthquakes that are subrayleigh, which is the usual mantra of seismology, to the next stage, which is basically the creation of the shock wave. And this is called the transition distance. We will see it in a case because we will calculate it for the gnarly fault. But if there is a building there suddenly and near the fault, and the rupture, the zipper goes by with very high speed, the shock wave will actually process this structure with effects that are not known or have not been studied in great detail. So, going back, this is the only thing that I'm going to show you with equations. I'm not going to discuss it in great detail. The point is, forget about the equations, just look at my hands. The rupture speed goes to, the rupture tip goes to the right, and there is shaking in the fault parallel direction and shaking in the fault normal direction. For subrayleigh ruptures, mainly the shaking is in the vertical direction to the fault. For supershear ruptures, theory says that it is fault parallel. And the ratio of the two, the delta ux over the delta uy dot, which is the velocities. These are velocities, jumps in velocities. The ratio is a very simple formula here, which depends on the rupture speed, the zipper speed, which is VR, normalized by the shear wave speed of rock. So what is happening is that the slip function on the fault is radiated out. But what I care is to look at the seismograms, resolve them in the fault parallel and fault normal direction, and see what is bigger. It's as simple as that. Of course, later I have to verify with the results from inversions. I'm not doing inversions. I'm not a seismologist. But it has to be consistent. So anyway, I will skip this. And to take you back to the lab now in another newest configuration, which uses a technique called digital image correlation, I would like to show you how these signals compare in the lab to the gnarly fault signals. So here is a movie. It's a combined movie. On top left, you see the fault parallel direction of an experimental rupture going to the right. This is experimental results, not theory. And the right one is the fault normal, and it plots, actually, the fault normal component and the fault parallel component as a function of time in microseconds here, and from that particular point. Okay. And what is interesting is just, again, without going into the analysis of all of this, is to compare it to what is happening in a much bigger scale here in one of the stations in the gnarly fault. And what you can see, there is equivalence, and what you see here is the fault normal component, the fault parallel component is higher than the fault normal component, which is a signature of Supershear. There is theory behind it, there's these experiments. You have to scale it, of course, properly with the material and scale to the Earth's crust. You have to be careful, but I want you to get a sense of what is happening here. So, but I had a formula from the lab and from the theory. Basically, if I know the ratio of fault parallel to fault normal, the vertical axis, and I know the speed of the rupture or of the zipper, I can get the speed of the rupture to be 55% more than the shear wave speed, which is 1.5. It's actually close to the dilatational wave speed, 5.146 kilometers per second. Imagine, this is a very fast entity. Imagine 5 kilometers and a second. This has gone this fast. And what it will do to the built environment next to it because of the shock waves. So here is the Mach cone, and this is what we have seen so far. But this happened it was recorded in the twin stations. The transition, since I don't have too many other stations, the transition from sub-Rayleigh to Supershear, the transition length that you saw in the other movie, the transition length is unknown, and perhaps we can calculate it, knowing the speed of when we caught the Supershear rupture. So this is what is done here. Very quickly, this hypocenter is here. The rupture goes up to here and changes speed, passes through our station. I know the time of arrival of the waves here. I can calculate with a very small, very brief calculation. I can calculate the transition distance from sub-Rayleigh to Supershear. Does it? I think it's. Yeah, it's working. Can you hear me? Yes. Yeah, it's fine. I will shout more. For the record? Yeah. Okay. So the first part, we know the speed is the classical Rayleigh wave speed. The second part, we know the speed because we just calculated from the formula. We know the total time, so we can calculate what the transition length is just from this. It's just algebra, and it's about 19.5 kilometers, call it 20, from the hypocenter. It decided to become very quick after that. So, okay, I don't want to actually spend time with this. So we go back and say, what is at this location? And we are very lucky again. We find another station at this location. And you know, there were only 3. So this is just luck. This is not good science. So, and we see there that there is another station. And at that point, actually, let me go back. I need a little bit of time. You see, actually, the pulse that is created in front of the rupture that has started going very fast. Okay. I'm going to finish very quickly, but I'm going to tell you what we did for the rest of the fault. This information allows us to create a model for the splay fault and to get the properties of friction in this small fault. But this is an immature fault. The question is, how do we understand the properties of the main fault and see whether it went to the right and left and whether it jives with the observations? So, let see, so I'll go there. Again, without going into any of the mathematics, we get the properties of the first fold, and then we reach the second fold. And what we know is that it went to the right. We also know that it went to the left with a delay, which we know. So we fixed the properties of the main fold by looking at the junction and running about 100 simulations, which you see them here. Some of them have properties that destroy the incoming rupture. So obviously this is not a good candidate. Some of them have properties that allow the rupture to go to the right only, and some of them are properties that allow the rupture to go both to the right and left. And this is the last one, which is this kind of properties that are acceptable. You see, it goes to the right, it goes with Supershear because you see the triangle, and in the left, a few seconds later, you see something created. It's being created and propagating to the left, and the timing is exactly what is set to be. The properties are manipulated in order to actually capture this. Let me show you now the general result. So this is the whole thing. So the rupture comes, it changes nature. You see the triangle forming now. It goes to the right as Supershear, and you will see it actually coming back, being generated in the left branch as well. Here it is. But in the left, there is no triangle. There is a butterfly shape, which is characteristic of the subrayleigh, the slow ruptures. So here it comes. And what I would like you to note here is what happens near the end. So it will go down, keeping that butterfly shape, but not transitioning to the shock wave. But when it comes to the complexity towards the end, it's going to do other things. So it's going to jump around, and it's going to regain in the end the triangular shape of Supershear, and there is Antakya. And it is the biggest destruction. It has nothing to do with the hypocenter location. I'll show it to you once more in the detail. Again, you see the map. On the bottom is Antakya. Perhaps you will allow me one more second to put two buildings. This is my civil engineering side, those with some of my collaborators. These are identical buildings. The design comes from Los Angeles. I will not tell you the address. And they are placed, hypothetically, next to the fault, at the same distance, 3 kilometers each. One is a slow zipper. The other one is the fast zipper. And I just want to see what the shaking will do to the slow one and to the fast one. So let me try and do this, and I will stop. Where is that? So you will see the top moving the first building, and it moves it first in the fault parallel direction, then in the fault normal direction. And then it cannot stand it and collapses. This is the fast one. The other one is the slower one, and you could see the rupture came later. That's why it didn't move initially, but it moves mostly in the fault vertical direction, and it does not collapse. This is just to demonstrate that things are complicated, that as far as the driving force is concerned, which is the shaking, the zipper speed matters, the hypocenter does not matter, the magnitude of the earthquake does not matter. Only the shaking from the zipper matters and the proximity to the fault. Thank you.
Thank you, Professor Rosakis, for this fascinating account of how mechanics can actually help us understand these dramatic phenomena over very large length scales. So we move on to the second speaker of the session, Professor Konstantinos Sinolakis. Professor Sinolakis is a member of the Academy of Athens, of the United States National Academy of Engineering, and of the Academia Europea, and he's a leading authority on tsunamis and coastal hazards. He's the Gordon S. Marshall Professor at the University of Southern California, Director of the Tsunami Research Center, Chair of Greece's National Committee on Climate Change, and former President of the Hellenic American Educational Foundation. Professor Sinolakis has combined scientific excellence with public service, shaping global standards for tsunami modeling, evacuation planning, and early warning systems. His talk today addresses one of the most critical dimensions of mega disasters, how scientific information is translated or sometimes fails to be translated into timely, actionable warnings and effective crisis management. Please join me in welcoming Professor Sinolakis.
Good afternoon. Welcome to all of our guests and, of course, to my colleagues in the Academy. I'm going to take you through a quick tour of my own journey and take you from fieldwork. I'm basically a theoretician, but over the last 30 years, I've done a substantial amount of fieldwork, and a lot of the explanations that I'm going to give you are based on the fieldwork where, I mean, we've been seeing time after time again that despite our best efforts in terms of creating fairly satisfactory prediction and forecast models, we are still not converging to the point of having saving people's lives and having no deaths. So let's play this, and I want to a little test for you at the end of the video, or rather at the end of my talk. I want you to associate all these images that you see, and there's a common theme in all of them. So this is our little test. But since we're in the Academy of Athens, and before we go in and talk about Plato, we're in a room where we have actually depicted one of the earliest huge and extreme natural disasters we know of. I mean, as you go around this room, I mean, this is the story of Prometheus. And if you go in, I mean, it's the birth of Prometheus. Prometheus steals the sun, steals the fire from the gods with the help of Athena. But over there is another part of the myth, very little known, where actually after Deucalion's floods, this is the Greek version of Noah's floods, Prometheus basically creates people again, and you see Prometheus there creating man, and there is Athena, of course, is always his guide. Behind me is the battle of the gods and the titans. I'm somewhere in the middle. Over there, it's Prometheus gives the fire to the people. Prometheus gets punished, and then he goes to the Hercules frees him, and then it's the apotheosis of Prometheus. So, in terms of extreme events and disasters, the ancient Greeks started pretty much around the 7th century to realize that natural phenomena, they were not there because they were God-sent, but because they were physical laws. And different ancient Greek, particularly pre-Socratic philosophers, started understanding and speculating as to this, to this phenomena, going all the way to the, to Democritus, and then Plato, who actually made a step sideways, because in his depiction of Atlantis talks about again about the the people being punished for being impious, which is exactly what we had escaped for about 2 centuries. And then, of course, Aristotle comes in afterwards and pretty much goes and sets the record straight. But in terms of, I have to acknowledge, again, we're in the Academy of Athens, the work of Spiridon Marinatos, who was an archaeologist, he was an academician, and he was the one who first connected the destruction of Minoan Crete, particularly not the palaces, but the demise of the Minoan civilization with the myth of, with the eruption of Santorini and, with Plato's Atlantis. So, I'll take you into this very, very quick trip in the last 30 years. I'll start, this is not my own field work, with the very first movie that we have of a tsunami, because the history of the tsunami hydrodynamics and how we try to actually get to the point of having early warnings teaches us a lot about how we should treat early warnings and particularly evacuation orders. This is back in, can you please start the video? This is back in 1946, April 1, 1946, Hilo, Hawaii. This was the only movie we had for pretty much 60 years of an advancing tsunami. Okay. Unfortunately, most of the people that you see here are dead. In fact, from all the people that you have seen in this video, only one person survived. This is an earthquake that struck in the Aleutian Islands in Alaska, close to about 3,000 miles away. Hawaii is pretty much in the center of the Pacific. It hit Hilo. This led to the creation of the Pacific Tsunami Warning Center, and at about the same time, this was in the late 1940s, early 50s, it is the time that the World Meteorological Organization gets formed, among others, to coordinate the issuance of warnings. The Pacific Tsunami Warning Center is formed primarily to be able to do earthquake detection and alerts, distant lands. I mean, if there's an earthquake in Alaska, alert people in Hawaii or in Chile or in Japan that there's a tsunami coming. So this is just the beginning, but then the system is only based, it's an earthquake detection system. Advance the clock close to 50 years. This is my first field trip, Nicaragua, 1992, where we do have this system in place, where we have this earthquake detection system. The earthquake is a very near shore earthquake. People don't, there's no time for a warning to go there, but also there's absolutely no shaking, no ground shaking, which usually warns people that the flood may be imminent. So this made us realize how much work we had, ahead of us, because if you had, literally only a few minutes, I mean, the tsunami arrived within about 6 minutes, to evacuate people, what would you do? And in this particular case, this was, an earthquake that basically completely blew our minds off, because it had an entirely different mechanism than we thought possible. It caused the shoreline to retreat first before advancing. To make a long story short, there are events after that. That earthquake forced the community, me, to reevaluate the models that we had for this particular, long waves, for tsunamis, the way they come in, etc. And we came up with a much more realistic model, which means if an earthquake has both uplift and subsidence, we needed to have a dipole type of wave, which has different propagation characteristics, and this would help us maybe have more targeted and better warnings if we had the system in place to get to those last 5-10 minutes before the tsunami comes in. So all this is happening, and this is later in 1995 in Manzanillo, very, very similar event. So we're building slowly this system, this computing capability, to be able to have warnings and to like cut down time, and be able to warn people in time for the tsunami flood coming in. And then the worst surprise of them all, where all the community is working around for the Pacific Ocean, and suddenly there's an earthquake in the Indian Ocean, and 250,000 people died. And this is from Banda Aceh in Indonesia. There was absolutely no warning, despite the fact that at the time, we did have adequate computational tools. And you can see here the tsunami just coming in from Sumatra in Indonesia. It's going to spread around the world's oceans. All of this technology existed in 2004. The problem is it didn't exist in the Indian Ocean. And even if it had existed, the local communities in Indonesia, despite all the events that had taken place, they were not set up to issue timely warnings. When I mean timely warnings, warnings within 5 or 10 minutes max. So, just to give you an idea how difficult these predictions are, this is a picture from Banda Aceh. This gives you an idea of how difficult it is to model these particular floods, because it's a debris floods. What you see there is a lot of debris. And look what happens. In the beginning, the wave propagates the wave front fairly slowly. People think they can outrun it, think that that car, it's trying to pass by. And within less than 30 seconds, you are going to see the wave, the flood accelerating. Try to model this computationally. But you are going to see now the flood accelerating. By this time, the flow is what we call supercritical, analogous to the Supershear of Professor Rosakis. And this is it. Not an easy wave to model, not an easy wave to survive. Nonetheless, it really helped us to go back and take measurements and try to understand one of the things that we want to know qualitatively and quantitatively, and it's extremely important for civil defense, is to know exactly how much time we have. I mentioned earlier, 5, 10 minutes. How much time is there? And this is very important information to relate to the local civil defense. They need to know how much time it will take for the wave to go up 1 meter, 2 meters, 3 meters. They need to know that because they can work backwards from it and they know how much time they have to do this warning. So these are the first measurements of an on-land tsunami flood that we made in Banda Aceh, of the order of 2 meters per second. These are very, very fast speeds. And then what you see there, or you have to spend time to see it, is the wave doubles its speed within about 30 seconds. Not the wave front, which is something, again, that local civil defense and people need to know, so they are not taken by this false sense of security that, we have time because the front is moving so slowly. They need to know that within 30 seconds, the wave is going to double the wave front is going to double its speed. Now, we thought that all of this, we had it pretty much under control, but then surprises never stop. 2011, Japan, and you see here the Hoku tsunami. What you see on the top, you see a seawall and the wave overtopping the seawall, and below it, again, the wave has overtopped a 3-meter seawall and is flooding the Sendai Plain. The top picture is from Miyagi. Why was it 3 meters? Because obviously their design height, what they had not anticipated such a big earthquake. Even in Japan, where earthquakes of magnitude 9 have happened in the past, they had designed their defenses for earthquakes for magnitude 7.5. Do not ask why. I mean, maybe they were, maybe naivety, or maybe stubbornness. Who knows? But this stubbornness and naivety not only costs people's lives, but it also costs children's lives. This is a school in the Sendai Plain, and I'm very, very upset when I say this, because this was outside the inundation zone, and yet it was flooded. What does this mean? They had inundation maps. This is Japan, after all. We used to think that they're perfect. Unfortunately, when it comes to natural disasters, nobody is perfect. We're learning one event at a time. So what happens in this school is, since outside the inundation zone, they do not have a plan for the tsunami because it's outside the inundation zone. Tsunami comes in. These are the effects of the students. About 60 students died there, and they keep it like this. It's almost like a mausoleum. the personal effects of the students. So this was a real tragedy because, as you can see here, computationally, and this is the lines that you see there, one on top of each other, these are the two leading models around the world. One is our own, used by the National Oceanic and Atmospheric Administration, called NOAA. The other one is another model called GeoClo. Both could predict how far the wave penetrated. This distance that you see there between the two, the blue line and the red line, that's of the order of about 5 kilometers, 3 to 5 kilometers. They could predict that fairly well. But nonetheless, unless you have the initial condition, unless you know what to expect, you don't. And of course, the biggest surprise was what happened with the Fukushima nuclear power plant. And there again, the aftermath of that was that it put back nuclear energy, whether you're a fan or not against it. I mean, I see it as, a necessary evil. We have to choose our poison. It put back nuclear power tremendously all around the world. And one of the reasons was under design. What you see here is from TEPCO's, the Tokyo Electric Power Company, that had designed the power plant. Their design height was about 6 meters. And to give you an idea how ludicrous, and I'm saying this fully understanding what ludicrous means, 6 meters, they see it in Japan about once in a decade. They have designed a nuclear power plant that you design usually with a horizon of 2,000 to 3,000 years for safety, with a wave height and with a tsunami height that you see every 10 years. Very weird. What we did with this, I don't have any time to play you this wonderful video, but we can go by, just like what we did in Banda Aceh, find places where videos were shot, and then try to figure out what are the velocities. And the outcome of this work, which takes 3 graduate students 1 million clicks to do, is something like this. And this is the first time that we see this tsunami hydrograph. This is the kind of information that we wanted to extract, and it's only possible for us to do it with field work, because analytically and with computational models, this is fairly hard to do, exactly because tsunami floods are exactly the way that I showed you, debris floods carrying cars, everything with it. What you see here is how quickly the water level rises from 0 to about 10 meters. And the one thing to notice in the horizontal scale is that all this happens in about 10 minutes. So the water level rises 10 meters in about 10 minutes. So this entire room would be filled with water in about 8 minutes, just give you an idea. And again, this is the information that we need to be able to move people out of harm's way in time. So we thought we were doing everything fine. I mean, by 2018, we had it, at least in the Pacific, and to a certain extent in the Indian Ocean altogether. We had evacuation warnings that could reach people, or at least if local authorities did their work, they could reach people on time. We knew Chile, 2015, 1 million people were evacuated in about an hour. People doubted what I said about Mati, that you could evacuate, and I'll talk about this, people within half an hour. 1 million people were evacuated within an hour. In California, 190,000 people get evacuated within about 30 minutes. And also in a fire in California, people get evacuated within, the entire Santa Barbara region gets evacuated in about 2 hours for a fire. So again, we think as a, as a disaster community, by this time I have started thinking also about fires and floods, that we're fairly close to actually having a reliable warning system. And then this happens in Indonesia, an earthquake. Granted, it was a very unusual earthquake of the kind that Dr. Rosakis said it's a strike-slip earthquake, the kind of earthquake that's not supposed to generate a tsunami. So there's no warning. We have an earthquake, 7.5 earthquake. There's no warning because they think the mechanism of the earthquake cannot really generate a tsunami, but it's a super shear earthquake. And what you see here is this poor guy saying, tsunami, tsunami, yelling, screaming. You see it coming, and you see the people minding their own business because, again, there is no warning. And people just go in, and the guy can see it coming. It says, tsunami, tsunami. And if we could see the whole video, he's trying to tell people, come up, come up. This is a shopping center where he's standing, and part of our work on the field is to go there, find these people, talk to them, try to understand what happened. So as I said, this is a strike slip fault. It turns out that it's Supershear, and again, we learned something. A few, pretty much almost contemporaneously, big hurricane in Florida. It is a really huge event, and you can see here how big the storm is. You can see what we call the Florida Panhandle coming in, moving in. There is evacuation warnings. In the United States, this is fairly weird in the sense that they give these warnings, but they don't, the local authorities are the ones, there's no centralized authority that are actually going to give evacuation orders. They're very, very slow in this, and of course, there is a long way to go. But what happens? Do people evacuate? No. About 60 people don't evacuate. I managed to talk to 2 of them, and this is the aftermath. People really, and this is the same story you hear from around the world, whether it's fire, whether it's flood, whether it's earthquake, whether it's tsunami, people will tell you the same thing. It has never happened here before. Of course it has never happened here before. This is the nature of the extreme event. If it had happened here, you would be prepared for it. But it's exactly, we have to be prepared not for what is likely to happen, and this is my mantra, but what is possible to happen. If we want to save people, we always have to think of the worst case scenario. So in Florida, obviously, they didn't. Mati in Greece in 2018, this is when I started modeling fires, and I'll show it to you. People, there are basically no evacuation orders, absolutely the worst conditions for a fire, very strong winds, descending winds from the mountain. It was known for at least a day in advance that these conditions would take place, extreme fire conditions. A fire starts, takes 2 hours to get to the beach. This is where people had to actually shelter from the fire. And again, the tragedy is that you can model this. These are agent-based models with a colleague from the University of Tokyo, Professor Tokugawa. And you can see this is, you can see how quickly people will evacuate, and if you let it run to 30 minutes, you're going to find out that had people known that you could have evacuation, they could evacuate to the beach, had they had any instructions within about this particular simulation, about 45 minutes. But this is starting from Neos Vutsas all the way to the beach, they could have evacuated. So we've run many of these simulations. Again, we think that we're doing better. After this, we know, and in Greece at least, we installed a 112 system, which is the emergency alert system. You get SMSs. This took a lot of effort, and I mean, it so happened that we had a government, particularly the Prime Minister, that was really interested in this and wanted to do it because there were tremendous opposition to actually get the system implemented, but it was. And it wasn't in the US, as you will see here in Hawaii, and this is Lahaina in Maui, very similar fire to Mati. This fire is 2023. Lahaina is the historic capital of Hawaii. It's on the right there. I'll show you one more picture. This is another picture of Lahaina. By the way, I saw these pictures to show this is what happens. Well, I mean, these are wooden houses. This house is about 80 years old. It was retrofitted the year before to become fire safe, and it's the only house that survived. This is for those people who think, oh, wooden houses burn. No, they don't burn. I mean, if you build it right, you can save it. But in Hawaii, they didn't issue any warnings, and about 100 people died out of 10,000, which is about the same ratio as in Mati, when you didn't have a warning, then about 100 people died out of 10,000. So as a result of this, and actually insisting and doing a lot of not just scientific papers, but editorials in the New York Times and the Washington Post that I wrote with my colleagues, we had in the United States the first emergency alert in 2023, October 2023, where it was a test, a nationwide test. In Greece, by the way, the first emergency alert was 3 years earlier. We were one of the first European countries to have an emergency alert system, literally, maybe the second or third in Europe, 3 years earlier than the United States. Are we finished? No. 2025. Altadena, California. Professor Rosakis' home is somewhere, was actually saved miraculously. It's somewhere on the right side of your screen. This is the fire burning on January 8th, 2025. You would have expected that at least after what the FEMA saw that what had happened in Maui, that there was no warning, that they would have alerted people on time, right? No. Obviously, I mean, this is, by the way, another picture of Altadena. This is not what they were expecting. Why? They were not expecting such a huge fire. What happens, again, why it had never happened here before? Well, if it had happened here, you would have expected it. Again, this is the same motto. And this is what happens, again, from another story from the New York Times. Western Altadena, here we have a case where in Eastern Altadena, this particular city that Professor Rosakis has his American home, in Eastern Altadena, there are evacuation warnings and nobody dies. In Western Altadena, this is a city of no more than 10,000 people. In Western Altadena, the evacuation warnings don't get there until 8 or 9 hours later, and about 17 people died. Again, why there is no warning? Warnings are there. We have the science. The science is there. What we're missing, and we see it time and time and time again, is the last mile, how we communicate this message in the last mile. And one more thing, Dr. Professor Theodorou. Again, we think that lessons are learned nationwide in the US. No, they are not. July the 4th, 2025, come Mystic in Texas, in a place called Flash Flood Valley. A flash flood is a very abrupt flood that happens primarily in late spring or the summer. 134 people died, but particularly 78 people died in a summer camp for kids, which was inside the river, and there was no warning system, even though the National Weather Service had warned for days earlier. To give you an idea how fast this particular flood was, you saw what looks like, I showed you earlier, tsunami hydrograph. This is a real storm hydrograph. This is technology that has existed for over, it started about 1870, around in Europe and around the US, has existed for at least 100 years, where you can predict before a storm comes in, approximately how quickly the water level will rise and drop. This existed, of course, this is after the storm, but in an area, if you look at my table there were historic storms that had reached that level. In 1932, 39 feet, that's 13 meters. In 1987, 38 feet. And yet, despite the fact that there were warnings, scientists were warning 2 days before the event, there's going to be flash flooding, etc., no action is taken. And this is again Camp Mystic. You can see in this particular cabins down there, this is where most of the deaths were. This is one of the messages. I don't have time to say it, but we come back to what happens in on December 31st in Crans, Montana, in the nightclub. Okay, this is a man-made accident, but again, what was missing after it all happened, the bartenders did not do what we had hoped, and it's our mantra to do. Tell people to evacuate, give them instructions, whether you're in a ship, whether you're in an airplane, whether you're in a bar, the people who are responsible should know what to do in an emergency. And even if you have started having a fire, you need to direct people and say, hey, you go over there, you leave right away, right now. Would people have died? Probably people would have died. Would 50 people have died? Probably less, had they known what to do. So, this is the end of my talk, Professor Theodorou. This is the sort of how the puzzle ends and how to put it all together, what I've told you from the beginning, in terms of, we exist on Earth because dinosaurs don't. Because why? Because, if dinosaurs existed, they would have eaten us. The reality is that we had the Chicxulub impact 65 million years ago, which basically did a planetary reset of the kind that we hope we're not going to see with global change. But if we listen to Professor Schellnhuber, that becomes increasingly more and more likely. this planetary reset, which, the planet is going to be there. The question is whether we are going to be there or not. And then this has to do with Achilles coming in, Achilles and the turtle. It's Zeno's paradox. No matter how close, and because the ancient Greeks couldn't understand uniform convergence of functions and how you can actually come to the end. I mean, Zeno was known for these paradoxes of how, you have a turtle and you give, competes with Achilles, and the turtle gets an advantage, and at the end of the day, Achilles is always behind the turtle because there's no uniform convergence. It's the same thing that we see with natural disasters. We try. In the beginning, we thought that it was always nature that's ahead of us. Now we know that it's human stupidity, a lot of the times ahead of us, which is exactly what we see, in climate change, and this is exactly what I encourage everyone to work on. Thank you so much.
Thank you very much, Professor Rosakis, for this fascinating overview of the importance of predicting and early warnings of these catastrophes. So we now go to the final speaker of this session. This is Professor Georgia Destouni. Professor Destouni is a corresponding member of the Academy of Athens and a member of the Royal Swedish Academy of Sciences, the Royal Swedish Academy of Engineering Sciences, and the US National Academy of Engineering. She is Professor of Hydrology and Water Resources at Stockholm University and guest professor in KTH. Professor Destouni's research spans hydrological extremes, climate-driven water cycle changes, and the cascading interactions between floods, droughts, ecosystems, and infrastructure. Her talk will explore how water-related hazards propagate through interconnected systems, often turning local events into regional or even global disruptions. Let's welcome Professor Destouni.
Thank you for this introduction. I'm very happy to see you all here and be able to talk about water. That's what I do. And you mentioned my affiliations, so I'm both professor of hydrology and water resources at the Natural Science Department of Physical Geography at Stockholm University, but also professor of engineering hydrology at Department of Environmental and Engineering, Science and Engineering, that's what it's called, at KTH, Royal Institute of Technology. And I mention this again because it shows the cross-disciplinary nature of this topic that I'm going to talk about. So water science and hydrology that goes across many different disciplines because water goes through all aspects of our lives, our societies, our economies, all ecosystems. And we need to understand how, in this particular talk, I'll talk about how extremes in water conditions, so too much water or too little water, how they propagate to have disastrous impacts. They become disasters because not all extremes propagate to disasters. And also things are generally changing in the world. Climate change and societal changes affect this propagation, and we need to understand that and how to predict, how to diagnose when extremes occur and how they propagate to disasters and how to project them into the future. So I will depart in this talk from a debate that's quite lively in my field, hydrology and water science. And in the age of artificial intelligence, that's another change we're in. And that started because we are now increasingly using artificial intelligence, machine learning in hydrology for modeling. And we have seen that using these types of models, they can often predict stream flows better than traditional physically process-based models. And that success is taken by some part of the community to question the relevance of hydrological science itself. And I would rather argue, and have done so in a very recent publication with a close colleague from US, Oak Ridge National Lab, where they have the most advanced models of hydrological and water resource models, that rather than showing the relevance of hydrological science, this success of AI, machine learning, reveals the unfinished agenda of science that is highly fragmented. And what I mean by that is that, and that's not just for hydrologists, that's water comes in to many other disciplines, and we need to understand what is going on. So what I mean by that is we have focused for a long, long time, and still, on isolated parts of the water system, so precipitation, some on evapotranspiration, some on runoff, some on this or that, engineered water systems, and have failed to connect the interactions between them. And that has led to inconsistent and context-specific, scientifically opaque predictions. And that's what we see the effect of here. That is not cured by using AI and machine learning, because those also focus on fragmented parts of the system. So to make progress and be able to diagnose, predict extreme events, but also the whole hydrological cycle and how it shifts along with other global change, we argue, and that's home-tail messages that I take up directly now, and I will clarify further in the talk, but we need to integrate data-driven and process-based models to coherently represent the terrestrial hydrosphere, so water on land, in a consistent, coherent way. And to do that, we need major enhancement of monitoring networks and data. So, starting with why the success of AI machine learning models, that success has been nearly almost only on predicting stream flows, but hydrology and water science is far much more than just stream flow, and cannot and should not be reduced to that. We need to understand water as integral part of the Earth system and its change, the global change, the societal impacts, and many different aspects of water. And we need different tools to be able to do that, modeling tools and data availability, and also to interact with stakeholders and communicate the implications of what we find. So, so water extremes, extreme events, are parts of these aspects, and the extremes of too much or too little water, flood and drought conditions, propagate to disasters through all of the many different interacting systems. And we need to understand that propagation across different scales and around different parts of the world to find some general patterns and the specifics of different regions and different scales. Another point, important point to remember, is that hydrology and water resource science, like probably most sciences, have dual roles. It is a fundamental earth science. That means we need to understand the flood and the drought and the compound extremes occurrence and their characteristics. But it's also a utility-driven discipline aimed to support societal decision-making, so we can plan and we can prepare and we can warn in time for extremes and their impacts and disasters. And we need the one to actually be able to do the other well. So we cannot get rid of the understanding and just advance on technological adopting AI and machine learning for very specific predictions. So we don't just need merely technological advances, but we need very much conceptual advances still in this science. So consistently advancing theories and data frameworks and models towards a convergence in realistically and similarly representing the integrated terrestrial hydrosphere. So I have a picture of this hydrosphere here, so you can see all the different fluxes that are involved in the global water cycle, and some of that cycling is taking place on land. And most of that water on land is actually not visible. It's the subsurface water, where 99% of the liquid fresh water on Earth resides. We don't see it. In a talk yesterday, we heard about, if you want knowledge, seek the unseen, the unknown. And that's exactly what we need to do here. And that's the part that we don't, our science, by fragmenting water and just going for what we see as water on the surface, we have neglected that part quite a lot. We have also neglected the connections. So we have some main fluxes on land. We have the precipitation, we have evapotranspiration back to the atmosphere, we have runoff, we have also engineered societal flows of water between the natural systems and our human societal systems. And if those fluxes are not balanced, we will have changes in water storage, changes in water level. That's something we will see when it happens for surface water, but when groundwater levels drop, and that's where most of the volume of water changes in storage, because that's where most water is. We don't see it, and unfortunately, we also don't follow it too much. And I give us one example here. So you see total runoff from land to sea goes through rivers. Yes, but before it goes into the rivers, it has been subsurface water flow, groundwater flow to the rivers to some degree. And if we look at different global estimates in the literature of how much the groundwater flow contributes to stream flows globally, we have an estimate range from 9% to 98%. We're talking 2 orders of magnitude. We're not talking, you know, a factor 1.5 or something. This is a major gap in knowledge. And it has not been discovered or emphasized because people are looking at their different fragmented parts and not putting everything together to understand how the flows and the storage changes are linked. So another point is that when we then try to bridge these gaps, which are very much related to the subsurface water and its interactions with what we see, we have the data-driven models, so AI, machine learning, and the process-based models, and they are not in opposition like much of the debate in my field has been about. So either deep learning or high-fidelity integrated process models, they are actually on a continuum. So we have the deep learning models that excel at pattern recognition, where large representative data sets exist. And we have the process models that represent processes at the right spatial temporal scales where they were actually derived. So they don't need to consider emergent effects of going between scales. And much of hydrology, however, and we need data for both the deep learning and for the high fidelity integrated process models. But unfortunately, much of hydrology, and especially the hidden subsurface hydrology, is fundamentally data limited. And I will show you examples of that. This is a paper just on its way to be published in Nature, where we have looked through all the precipitation stations existing on land, and we have seen some very major gaps globally in monitoring networks that really hinder our possibility to assess climate change impacts on the water conditions and the extremes on land. So we have only, just to have some highlights, we have only a little more than 30% of the global land surface currently meeting WMO, World Meteorological Organization requirements for annual precipitation modeling. And we need very strategic investments to actually place new monitoring stations where they are most needed, where we expect to see the greatest changes forward. And we need the data to be openly accessible. That's another hinder. And you can see here a red circle or ellipse in the area where we are now. So Eastern Mediterranean region, unfortunately, is a region with very low data record, very short records if they are available openly. And you see on the bottom graph here that this is also a high priority level region for actually investing in new data, precipitation data monitoring. And things are even worse when we go to the other flux components, because we need to and want to link them. So here we are looking at catchments around the world, the colored fields, where we have a multi-decadal stream flow monitoring data continuously, at least from 1985, at least monthly, from which we get the runoff data, or can calculate the runoff. And the monitoring that is there that fulfills that criteria covers only 27% of the global land area. Again, you see Eastern Mediterranean, and in fact, the whole Mediterranean region is a white hole here. No data, we cannot assess anything, at least not openly available. Okay, so another point to make is that the AI and machine learning modeling is transforming process-based modeling as much as it challenges it in this field, because we have great use of AI, ML-powered tasks that can be done in modeling, so data imputation to fill in gaps where we can do that in data, parameter estimation, surrogate modeling, downscaling of climate projections, computational accelerations, all that we can do with the help of AI and machine learning. And that enables, in turn, better process and model representations that are more realistic, scalable, and transferable. So we need both of these parts to go forward. And I can give you another example here of a paper looking at drought propagation through the terrestrial water system. What you see around the world, so what you see to the left are examples of correlations between evapotranspiration and soil moisture at peak of droughts. So we could get the global picture based on observational data by data imputation, AI, ML powered. And you see the correlations on the top left based on observational data, and on the bottom left based on climate and land surface models, an ensemble of models. And you see that the results are very different. And what the data, the climate and land surface models do not capture is that we have very different drought propagation if we are in a wet region or a dry region of the world. So if we are in a wet region of the world, so like Sweden, where I come from, when you have droughts, it can actually be very positive for your crops and vegetation because we have mostly too much water, and that's why we have drained the land so much. So actually, at some level of drought, that's only positive. Of course, it goes further, depending on duration, intensity, and so on. Then we start getting damages there, too. When you are in a dry region, you have a very different, you have the soil moisture, the drought anomaly going directly to the vegetation and crops and damaging them. So these are very different responses to drought of different parts of the hydrological cycle. What they also reveal, this data, is that we have an overall closer association of soil moisture with runoff than with evapotranspiration. So soil moisture goes at least as much to feed groundwater and runoff as it does to feed evapotranspiration, so plants and vegetation. That's another thing the climate models and land surface models do not capture because they don't consider lateral flows, in particular not in the subsurface. So out of sight, out of mind there, because they are considered not important. Another thing, example of what we can do with the AI, ML modeling, strengthening data and calculations we can take from a relatively data-rich region, so Sweden. You see here to the left, actual data for documented extreme event occurrence. We looked at droughts, floods, and heat waves, actually, also, from 1922 to 2022, so to learn from the past so we can develop some warning and understanding for the future. What we can do with that is to then identify hotspots of droughts, of floods, and trends of floods, droughts, and heat waves, but I'm just showing you some of the results here. And the different aspects we're looking at is intensity, duration, frequency of these extreme events across those years. And this can let us plan for where to focus preparations and plans for meeting drought and flood events and heat waves, in fact, also. Then we can propagate this further, looking at the connections with human systems and economic sectors. So we calculate, we look at the times when we had severe events, and then look at effects. In this case, we are looking at annual losses to gross value added nationally. So we can, this has been done for every municipality in Sweden, then aggregated to national scale, and you can see how these losses that one can statistically relate to these events are distributed over the years. In summary, we can see that the flood events occurring in Sweden between 2005 and 2022 have an annual cost of 4.1 billion euro. Drought come after that, 2.9 billion euro, and heat waves, 2.3 billion euros. And we can do these associations also, and have done with infrastructure, stability or failure, and public health effects. So we can, for example, see effects of droughts on morbidity, even though those are not as dramatic as having a tsunami coming over land, but you still have them, and they're just more difficult to detect. Nevertheless, we can do all this with the help of modeling, strengthened with AI and machine learning, but we still don't understand the mechanics. I mean, we just have the statistical association. So if we want to diagnose why these extremes occurred, where and when they occurred, and how they're going to occur and change in the future, now we need to go to processes and understand them. Okay, this is just another picture of these cascading impacts, economic impacts, now divided in different sectors. So I'm not going to go into the details of this, but you can see that we can distinguish specific sector effects, so can help the sector's planning. Okay, so now comes the real difficult part, is the non-stationarity in the changing world of how things actually interact, how to extrapolate to unseen conditions and the future role of models. On the other hand, we have the deep learning that has performed very well for some parts of the hydrological cycles, but we have no evidence that that representation can actually extrapolate reliably into unseen conditions. Dissimilar regions are outside the model area of training and applicability and to future climate and land and water use regimes that may not have present-day analogs. And then we have, on the other side, then the process modeling that is gaining in importance to understand these mechanisms. But we still have to live with the data gaps. I showed you knowledge gaps and deep uncertainty. And I'm finishing. This is another way to represent the hydrological cycle than you may be used to, but it's a way of focusing on interactions. So this is a network-based representation where the nodes are distinct types of water systems, so surface water, groundwater, vegetation water. Edges between are the flows between the subsystems. And we have looked at how different global models of the terrestrial hydrosphere represent this network. Some of the flows here are explicitly reported by the different models, and some are implied by water balance. And you can see here just in numbers, and I have circled here the groundwater fluxes, where you see that the uncertainties are of our greatest, actually, for the groundwater fluxes, the linkage with surface water, and the soil moisture distribution of water to groundwater rather than to plants. This is another way to show the uncertainties and the means of the different fluxes, and we can see that the greatest flow uncertainties, greater than associated with precipitation, evapotranspiration, anything else, of the big flows are related to groundwater, subsurface water flows through soil and groundwater. So we need to recognize that, because that propagates in how we understand the global hydrological and local, from local to global. And these are showing how different widely used data model representations of hydroclimatic variations in space, how they manage to represent mean temperature. That they do very well. All models and data sets agree very well. Then they start to diverge when we come into the terrestrial water fluxes. So precipitation, runoff, evapotranspiration, you start to get very different results. And then when you look at that blows up when you look at, put everything together and look what they imply for mean storage change. So you see in the panel E here, you can see the curve, the magenta curve is the era 5 representation of drying or wetting of the terrestrial hydrological conditions. And you see that it's totally unrealistic and different from other data sets that actually honor the terrestrial water balance. So that would imply that we have continuous 30-year drying globally on average over the world. And you can see, I mean, we don't have it. So this is entirely unrealistic. This is what many use to understand what is happening with hydrological conditions on land. And then this is a bit messy, but I'll just say this is when we looked at the different data, model, representations, machine learning models, at how the different water fluxes, precipitation, evapotranspiration, runoff, have been changing over the last decades in different parts of the world. And we asked the question, does the integrated terrestrial water cycle intensify or weaken with the warming that we have experienced? And the answer is, it does everything. You know, some part, just 20% of the land area, we see intensification, so acceleration of the cycle. In a bigger part, we actually see weakening of the cycle. And that means that so full intensification means all fluxes have accelerated. Weakening means all fluxes have weakened, but what happens mostly is both. You may have acceleration in precipitation, but and in evapotranspiration, but weakening, deceleration in runoff, and all kinds of combinations. So more than half of the land area experience very mixed conditions, and the terrestrial water cycle and its extremes are very difficult to assess because of this lack of data on the very complex interactions that we have with changes happening in all directions. And I'm just finishing with this a full complexity water cycle in this network-based approach, where we are very, very far from understanding these interactions based on the data that we have. And in particular, all the magenta edges, so fluxes you see here, are engineered societal water fluxes, and how they interact with a natural water cycle to change the conditions for both is something we are looking at. Thank you.
Thank you very much, Professor Dastuni, for this excellent talk that shows the importance of correct multi-scale modeling of water resources and the complementary role also played by process and modeling and artificial intelligence. So I hope you will agree with me that all three talks have been excellent and very illuminating. And let's please thank all speakers once more.